All right. Welcome back, everybody. I see we are down to people who haven't left for spring break yet. If you remember from last time, we were talking about a couple of things. I wanted to refresh your memory a little bit here. One was precise exceptions, was an idea that I introduced when we were talking about paging. This is a generally important idea, which is the idea of a precise exception is that the state of the machine is basically preserved as if the program executes every instruction up to a well-defined exception point, and that instruction that caused the exception and everything afterwards acts as if it hasn't started. Now, if you were to take a 152 or take some other class where they talk about processor design, you could see that the other instructions might actually have started and even finished. As long as you unroll them properly, you can get back to a precise exception point. But the reason we want a precise exception point was exactly so there's a single point in the program, we just restart there and we're good to go. We don't have to worry about anything being partially executed. Okay? And imprecise exceptions are basically anything that's not precise. That's not entirely surprising. The key thing to know about imprecise exceptions is that typically restarting an imprecise exception is very challenging. And so the operating system code around an imprecise exception is typically quite complicated. Okay? Because there isn't a clean instruction. You may have to restart some instructions, but not others. You may have to restart half of an instruction, whatever. And there are reasons that processor designers might design some of the interrupts to be imprecise. For instance, divide by zero is a great example of something that you may not want to recover from very frequently, and so going to the trouble of making it precise might not be worth the trouble, okay? Because you're not going to recover from it. Most page faults or TLB faults that I know of are all precise. I haven't run into one that isn't, so that's kind of nice. And the other thing, final thing I mentioned on this was that out-of-order execution techniques that lead to allowing you to do branch prediction typically also get precise exceptions. All right, were there any questions on this idea? Okay, you'll run into this again. The other thing we talked a bit about was demand paging mechanisms, and we were basically talking about how once we've got page tables, the page table entry can be used to essentially let us treat memory as a cache on disk. Okay, and there's these two bits, valid and invalid, or present and not present, depending on what architecture you have. And valid means the page is in memory, and invalid meaning it's not. And what you can do is you can mark pages that you want to have out on disk as invalid, and then as soon as the processor tries to touch them, you get a fault, a page fault, and the operating system takes over, pulls it back into memory. Okay, and so I showed you last time, I gave you this little pink box that kind of showed why this is like a cache miss. So if the user program references a page that has an invalid PTE, the memory management unit traps to the operating system with a page fault. The operating system now takes over its page fault handler. What's it do? First thing it does is, since it's going to pull a page off of disk, it's got to find a place for it. And so this, choose an old page to replace, there's a lot of interesting complexity in one sentence there. And we're going to talk a lot about that in the middle half of this lecture. Okay, so we find an empty page. And if that empty page happens to be dirty, before we can overwrite it, we better push it back out to disk. Does that make sense? Why do we want to do that? Yes? That's right. The page has got valid stuff in it. If we just throw it out and write something else on top of it, we're going to lose that stuff. So if the D bit is, the dirty bit is 1, we're going to have to write it to disk. And then we're going to mark the page table entry pointing to that page as invalid because whatever process owned that page doesn't anymore. We just took it away. Okay, so the first 3 things I've got here are all about freeing up a slot to put something into, and then we go to disk, grab the page that we missed, we update the page table entry to point at that page, and we have to typically invalidate a TLB there too to make sure that it doesn't say this page is no longer valid, because it now is. And then we start the thread over. So these 6 little items here are really the cache miss or caching aspect of this technology. Were there any questions on this? I went through it last time. I wanted to just make sure we said something about it again. Everybody clear on this? Do you see how there's a couple of places where TLBs have to be invalidated? Pretty much any time you modify anybody's page table, there's usually TLB invalidation going on somewhere. And if you're doing software TLBs like we used to do in the Nachos projects for this class, you got to be really careful because TLBs are completely managed in software. Okay. All right. And so then other interesting thing was when you pull things off of disk, you let the process sleep because it's going to take 1 million instructions for something to come off of disk. So why waste it? All right. That is how we do demand paging, where demand paging is treating memory like a cache on the disk. What we're going to do today is we're going to talk a lot more about this idea of choosing the old page to replace. Okay? Because that's a surprisingly complicated decision since going to disk to find a page is so expensive. We got to be really careful about which pages we throw out. All right. And so here was the summary. This is from the Dragon book, but it's a good picture about what happens with a page fault. You do a load instruction that has reference in the page table that's marked invalid with an I that causes a page fault trapped to the operating system. The operating system discovers that the page is on disk somewhere in the backing store. So we go to disk and we bring it in. Notice how I've just said free frame here. I've sort of completely covered over the notion of how we found a free frame. And then we reset the page table to mark it as no longer invalid, and we restart the instruction and we're good to go. And by the way, this restart instruction is made easy because the instruction has given us a precise exception. Okay. Just tie those all together. Good? So this is kind of the state of where we are. Now, I did want to bring this picture up once again. Remember, the reason I brought this picture up before was we want to have the size, look like we've got the size of the largest item with the speed of the smallest item, and that's the whole point of caching and locality. But what's kind of interesting about this memory hierarchy is that some of these items are exclusively managed in software and some are managed in hardware. So, and notice also that some of them are accessed in hardware. And so the processor accessing registers, that's done in hardware. If it does loads or stores to memory, all of this L1, L2, L3 is typically done transparent to the process or to the program. So the program says load, and it automatically decides whether the data is here, 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 or in memory, and that part of the caching process isn't something typically managed by the user program. Okay, that's all done in hardware. And if you take a 61C, they talk a lot about hardware caching. We talked about hardware caching last couple of lectures. And this is transparent, okay? So the only way you can kind of optimize for this is to somehow improve your locality of reference in your program or rearrange the data in your program or whatever. That's about the best you can do. Now, so I would call all of this stuff kind of hardware managed, all of the tags, all of the motion, etc. The rest of this is pretty much software managed. So where you place things in DRAM, where they are in, say, the secondary SSD, where they are on disk, all of that stuff is software managed and actually accessed typically with software instructions knowing where things are. So there is a pretty big difference between the hardware managed and the software managed. And for the lecture today, and kind of moving forward with I/O, we're really kind of talking about this software-managed side of things. We're going to be moving things around in software. We're going to pick which pages come off of disk and which go back to disk. Yeah, question?
Is there some reason you haven't included registers in?
Well, gee, let's talk about that in 1 second. So we have page table entries also appear in there. So, we also didn't include the TLB, and we've got this green thing that for some reason I didn't cover it. So why... Is that managed in hardware or software? Is it accessed in hardware or software? What happens to that green box? And why did I not include it in my original boxes? Who manages registers? CPU uses registers. Who manages what data goes in what registers? Huh? Program. Compiler. Right? So you'd say the registers are kind of software managed. I would say they're not hardware managed, but they're hardware accessed. So it's kind of a funny category. Who manages the TLB? Software. Hardware. Well, both, right? Because we talked about how the memory management units on most processors today, including the x86, do hardware table walks. When you do a TLB miss, they automatically pull things out of the page table into the TLB. But there's a lot of instances where you have to flush the TLB in software. So the TLB is a funny kind of half hardware, half software managed thing. So this green strip, the reason I didn't originally include it, and the reason I put a question mark up there, and the reason I paid the gentleman in the fourth row there to ask this question is it's kind of a hard category to figure out there. Those are kind of interesting items. All right. Questions? Okay, so some questions for the rest of the lecture here. During a page fault, where does the OS get a free frame? Okay, I don't know. Keeps a free list. Runs a Reaper if memory gets too full. If it's last resort, evict a dirty page first. Well, these are some options. Let's see if we can figure out what's actually going to happen. Okay, and I'm going to give you some ideas of what goes on. And we're going to want to try to organize these mechanisms. And in some sense, we're really working on a replacement policy in all of this for the memory. And then we might also ask this question, how many pages do we actually give for each process? And this is really memory scheduling, very much like thread scheduling. Okay, we got to figure out, is this a fairness thing? Do we fairly give the same number of pages to every process? Or do we have priority? Certain processes are more important than others. Okay? How does that go? Some processes are more equal than others, right? You guys all remember that book? Maybe it wasn't quite worded that way. And how about allocating disk paging bandwidth? This is actually a funny denial of service hole in a lot of operating systems still, which is, even if you say process A and process B get equal amounts of memory, if process A is using its memory poorly and paging all the time, it can actually screw up process B's access to memory, even though we divide them evenly. And the reason is that process A is busy using all the disk bandwidth to page in and out, and process B gets screwed up by that. It's denied service. Okay, and most operating systems don't directly address that, even though they really should. Okay, so let's move forward here. So let's start by really hitting home this notion that demand paging is caching. So I'm going to come up with the effective access time, or EAT, which is the hit rate times the hit time plus the miss rate times the miss time, or the hit time plus the miss rate times the miss penalty. Now, why are these two things typically the same? What have I done here? There's an essential assumption built into the fact that I put these as equal. Yeah?
The miss time is greater than the hit time.
Not only is the miss time greater than the hit time, that's certainly true. What else about it? Yeah.
You're always doing the work for the hit time.
Yes. The miss time includes a hit time plus a penalty. So typically what happens is, well, I missed, I got to go get it, that's my penalty, then I got to do the hit work. Okay? And so this second one is probably an easier one to deal with, where the penalty is really what's the penalty for going out to disk. And here's an example. We got some DRAM. It's got a 200 nanosecond time, which is getting pretty long in the tooth now. That's a few years old. It's got an average page fault service time, let's say, of 8 milliseconds. That disk is also maybe 4 years old. And suppose that P is the probability of miss and 1 minus P is the probability hit. That P is very timely because P is P. And so then we can compute the EAT time as follows. We say, well, it's the hit time, plus miss time times 8 milliseconds. And notice, milliseconds and nanoseconds are different. Milliseconds and nanoseconds are different measures of time. There's how many milliseconds in a nanosecond? A million, you can see that right there, right? So there's a million nanoseconds in a millisecond. And so we basically have to make sure our units are all the same. We work that out. And what we can see here is that if one access out of 1,000 causes a page fault, then this time is basically 8.2 microseconds, okay, which is a slowdown by a factor of 40, over what it's supposed to. So 200 nanoseconds is 0.2 microseconds, okay? And if you want the slowdown to be less than 10%, we can do that calculation and come up that we need basically one page fault every 400,000. Okay, so P has to be 1 over 400,000 in order to get only a 10% slowdown from this particular scenario. So I hope that hits you home a little bit, right? That says that I better never page pages in or out, or I'm basically dead in the water. Okay? Basically having a 0.1% page fault rate slowed me down by a factor of 40. Yes? Well, unfortunately, there are no really good realistic miss rates because it depends on the application. Today, pretty much if you're swapping at all, you're dead in the water. And so this 1 in 400,000 is certainly something that you strive for. Yeah, this if you're ever wondering and you see your disk flashing a lot and you're wondering what's going on, you're probably swapping a lot and you're probably in this serious slowdown realm, okay? So the goal, of course, is to never be slowing down with swapping. You really want swapping to be something that's purely letting you get the unused pages out to disk, not get pages that are in use out to disk. All right? Any questions on this? Question? No, just, okay. So, what factors lead to misses? Okay, we said this before, right? Compulsory misses. But in this case, a compulsory miss, pages that have never been paged into memory before. So how do you get rid of these misses? Well, we might actually, as we're starting a program up, we might prefetch a bunch of pages that we know we're going to need in the future. That would get rid of compulsory misses, right? Other misses we've talked about, capacity misses, not enough memory. Well, what do you do about increasing memory size? So one option is you stop your computer, you plug another DIMM in, and you got more memory, right? That, unfortunately, is a rather inconvenient thing to do because you got to turn the computer off and you also got to, wait your 2 days for Amazon Prime to give you your new memory or wherever you buy it from. So I guess you could drive to Fry's, then you're good to go, right? Another option, though, is really adding memory is more about partitioning. So if you got a lot of processes, you could try to give more memory to ones that are swapping more. Okay. Conflict misses. Okay, technically there are no conflict misses in virtual memory because it's fully associative. We talked about that last time, right? It's a fully associative cache. The final thing, though, is much more interesting, which are policy misses. And these are misses caused when the pages were in memory, but they were kicked out prematurely because some policy decided that they ought to be kicked out in honor of some other page. Okay, and that's really the flip side of this. How do I know which pages to replace? Well, I want to replace ones such that my policy of replacement doesn't cause a lot of misses on some process it's going to notice. Okay? Or the flip side is my page replacement policy is a source of policy misses. Okay. Now, so what are some page replacement policies? Well, why do we care about the replacement policy? Well, replacement is an issue with any cache, but it's particularly important with pages simply because the cost of being wrong is high. 1 million instructions lost if you pick the wrong page to throw out. Okay, so it's something we want to be careful about. And you want to keep important pages in memory. And so we could come up with some simple policies, and let's do this just because we can really quickly. So we could have a FIFO policy. So you take all of the pages, you take all of your DRAM, you divide it into 4K pages, you line them all up, and you page out the first one, the second one, the third one. You just work like this, and you just keep going around and around and around, and you just keep replacing in FIFO order. Okay? This seems on the face of it to be just a really dumb policy because, you're indiscriminately throwing out good pages and bad pages with absolutely no care in the world. Okay? Min is a really cool policy. The min policy says only throw out a page if it is the one that won't be used for the longest time in the future. Okay? We always like policies like this. The problem with this policy is you have to know the future. By the way, I'm a strong advocate of knowing the future. You've probably started to figure this out. Yeah. So this one, you got to know the future. The good thing about it is, of course, that it becomes a guaranteed not to exceed kind of policy to compare against. And then random. Pick a random one, throw it out. This, remember, worked really well for caches when the number of lines in the cache were relatively small. Random was actually not so bad. The problem here is we have so many pages and the cost of being wrong is so bad that random is going to turn out not to be good either. And the thing is, it really makes the running time of processes unpredictable because you don't know whether they're going to have their working set in memory or not because every run's a little different. Okay? So, for instance, if you have real-time requirements on some process, random is going to give you, non-guarantees. Okay. Here it seems like a good one. Least recently used. Replace the page that hasn't been used in the longest time. Okay. Now LRU is a policy everybody likes to bring up. So programs have locality. So if something's not used for a long time, it seems pretty good. And it seems also, if you think about it, that LRU is probably a reasonable approximation to min under a lot of circumstances. Reasonable. Now, the problem with LRU, of course, is what? What is the problem with LRU? What is that? Hard to what? Oh, keeping track. Yes. Okay. What about keeping track? Okay, the overhead. Now, how many people have ever built a linked list data structure? Okay. Now, we can imagine that the way you might do LRU is you build a list of all the pages, and there's a head and a tail, and how do we implement paging with LRU if we have this list? What do we say? Every time we do a load or store to a page, what do we have to do? Take the page out of the list and put it where? To the front, the head. Okay, so this is, on every use, we pick the page that we've just used, pull it out of the list, and put it at the head. So if you think about it, what we are saying is that somehow a load or store turns into a bunch of pointer operations and a rearrangement of this list, and then the load or store, which seems like we've just gotten ourselves back to the same mess that we had with the page table that we used a TLB to get out of, right? This one is not going to be as easy to get out of. And the problems are really the fact that the manipulation operations are more expensive than the things we're trying to track for LRU, and so that's a problem. All right. So people in practice actually don't use LRU. They approximate it. We're going to say more about that in a moment. Okay. Anybody want to guess how you approximate LRU? I saw a few people doing this. Is that a wax on, wax off sort of thing? I guess you guys are all too young to remember that. How do we approximate LRU? Okay, I hear clock. All right, we'll say that in a moment. So let's look at a couple of these things just so we're all on the same page, so to speak. So suppose we have 3 page frames and 4 virtual pages. So 3 physical frames, 4 addresses, and we're going to access address A, B, C, A, B, D, A, D, B, C, B. Ooh, that's got a beat. So here's a FIFO page replacement policy. You ready? So we have at the top the references to A. We'll pick frame number 1 since we haven't had anything in practice. B comes along, we pick number 2. C comes along, we pick number 3. Now the way to interpret this bar is that A has been in page 1 the whole time, B has been in page 2 here, and C's been here. And so now when we come along with A, is this a hit or a miss in the page table? It's a hit, right? So we're good. B comes along. Is this a hit or a miss in the page table? Hit, right? We win. D comes along. Is this a hit or a miss in the page table? Miss. Now the FIFO policy, which page is it going to choose to replace at this point? Right, page number 1, right? Oops. Okay, so we replace number 1. So this is a page fault. Okay, we come along with A. Which page is it? Well, is that a hit or a miss? Miss. Which page is it going to replace? Right, number 2. Okay. D comes along. Is that a hit or a miss? Hit. Good. B comes along. Hit or a miss? Miss. Okay. C comes along. Hit or a miss? Miss. Okay, so does everybody see what we're doing with FIFO? We've basically taken page 1, 2, 3. We've considered in a ring, and we just replace number 1, number 2, number 3, number 1, number 2, number 3, and we just keep going like that. Okay, so the good thing about FIFO, easy to explain, easy to implement. Bad thing about FIFO is it's just a bad policy, and I'll show you why in a moment. But in this particular scenario, we've got 7 page faults throughout this. You can count them 1, 2, 3, 4, 5, 6, 7 places where we've changed pages. Okay? And notice that when replacing D here, replacing A was a really bad choice because the very next thing we did was go for A. Okay, so replacing A there was just a bad idea. Does everybody see that? This was just a bad page to replace. Okay, what would have been a better page to replace? Okay, probably C. Okay, because that's the longest one. That's the farthest one away in our time stream here, okay? Good. Now let's look at what min does, same thing. So again, you guys have already figured it out. A comes along, we're good. B comes along, we're good. D comes along, we've decided we're going to replace C. Voila, good. A comes along, we're good. D comes along, we're good. B comes along, we're good. C comes along, okay, we got to replace something. Okay, 1, 2, 3, 4, 5 faults, okay, so it's better. Okay? Everybody with me? Good. You guys are right on top of things now. So what would LRU do in this? It turns out it's going to have the same decision as min, but that's not always going to be true. But in this case, LRU actually equals min. So there's a good statement of why LRU and min are the same in many cases. Now, when will LRU perform badly? Well, you guys can already figure this out. Consider A, B, C, D, A, B, C, D, A, B, C, D. Okay, A, B, C, D, A, B, C, D, A, B, C, D. Every reference is a page fault. Okay? Ouch. Why is that? Can anybody give me an elevator description of what happened here? That's a description in one sentence. In an elevator. What's an elevator level description of what's wrong here? Okay, sequentially accessing the file. What else? That's not quite the sentence I'd choose. It's close though. I think I would say that the working set here is bigger than the size of memory and we're sequentially walking through everything. I think that would be a closer explanation of what's going on here, right? Because the working set is so big, when we sequentially walk through, there's never an LRU that gets to stay around, and so we lose. Okay, so that's bad. What's interesting is min does better on this one. So this is a good example where min, knowing the future, doesn't fall into the same trap that LRU does, knowing only the past. So once again, if you can know the future, you're in great shape. Okay? What did you learn in 162? I learned that it'd be great to know the future. Okay, what else did you learn? So, any questions? Okay. So what we'd like in general, by the way, is something like this, that as we add memory to a process, the page faults go down. Wouldn't that be great? That's kind of the idea we would like. And does this always happen, that adding memory causes the number of faults to go down? Okay, in the limit. Well, it turns out that there is a replacement policy called FIFO, where it's not actually true, and it's called Bilaty's anomaly, and you can actually show that adding memory makes things worse in the FIFO policy, okay? And actually, let's look at this one. Here's a case where we start out with 3 pages and we go to 4 pages and we do FIFO. What you actually find out is there are more faults in the blue case than in the green case. So FIFO does worse with more memory than less. Okay? So there you go. That's another one of those party things, right? Did you know that there's this thing called Bilaty's anomaly? You guys are going to be party animals by the end of this class. But LRU and MIN have the nice properties that they really do. When you add memory, they retain their previous properties plus do a little better. So that's why LRU and MIN are by far preferable, and LRU being the only implementable one of those two is far preferable to FIFO. Okay, so FIFO is just a bad idea. Okay, questions? Okay, I know there's people busy counting. You'll find there's more faults in the blue one than there is in the green one. Okay? Okay. So, how many people got bit by the website last night? Okay. How many people had it ruin their dinner and their day was just awful as a result? Oh, I'm sorry. I apologize. We ran out of memory and then it crashed and then a bad checkpoint got restored and so there was a phantom homework 3 that appeared. Believe me, that server was having a bad day. The TAs were not too happy either, but I think it's all fixed, so I apologize. If you thought there was a weird hard homework 3 that showed up, it's weird because it was last term's homework 3. So anything you pulled off of the website yesterday, you should verify is still what you expect, because it certainly wasn't during the weird problems yesterday. Okay, no sections this week. We decided that we ought to give you guys some breathing space, and sections we're getting a little bit ahead of lecture anyway, so no sections. Okay, so you can enjoy the Thursday and Fridays that you would have worked so hard with. And of course, spring break is next week. How many people were not aware that spring break was next week? Nobody? Okay, good. No classes. I know I won't be here. You're welcome to come here if you can get in because it's probably locked, but you could sit in the row that you normally sit and watch a blank screen. That's fine. I suggest going somewhere else. We're still grading. Excuse me. The solutions I promised you on Monday are still as done as they were on Monday. They're going to be posted off of a handouts link. I'm told anytime now. The problem is the new website is different than my old one. There isn't actually a handouts page. And so there was no place for me to post them. But there will be a handouts page with the solutions posted. And I'll tell you, if we don't get them soon, I'll post them to Piazza or something. So those of you that really want to look over the solutions can. I apologize for not getting them into your hands. Partially, this was a problem because the website was so screwed up. As I also mentioned last time, Checkpoint 1's been moved to after spring break Monday. So this will give you guys a little bit more breathing room too. So we're really trying to encourage you to not come here and stare at a blank screen during spring break and actually take a little time off. So any other administrative questions? No. Thanks everybody who responded to the survey, by the way. I don't know if it's still open if you haven't, but it's very useful. It helps us improve what's going on in the class too. So if you didn't get a chance to respond, it's probably still an active link, so give it a shot. But we definitely like to hear feedback from you guys. So, all right. So let's talk a little bit about LRU. So one way to implement LRU is to timestamp every reference and then keep a list of pages ordered by the time of reference. And unfortunately, this also isn't a way to implement LRU quickly because it's too expensive to implement. So let's see if we can come up with something else. And this is the clock algorithm. All right. This is the Karate Kid of LRU implementations. You basically arrange physical pages, all of them in a circle. And then we think about a single clock hand working its way around. And we're going to approximate LRU with this. And the important thing about the clock algorithm, in addition to it being ordered like a clock, and I'll show you a picture in a moment, is we're going to replace an old page, not the oldest page. Okay, so we're going to let ourselves relax this LRU notion of getting the least recently used page, and instead we're going to replace just an older page, okay, and that'll be kind of our goal, and that's going to make this implementable. And the details are as follows. Remember in the page table PTE we had a use bit for every physical page, and every time the processor uses that page table entry, the use bit goes to 1. Okay? Now, that doesn't seem very useful after the first reference. So the point is the software is going to set it to 0, and then we're going to look later to see if the hardware set it to 1. Okay? And forget that reference to nachos there. I forgot to remove it. So on a page fault, we're going to advance the clock hand and try to find a page by checking the use bit on the next page, and if there's a 1 there, the page is busy and we're not going to bother it, and if there's a 0, we're going to consider it not interesting enough to have been touched since the last time our clock hand came around, and therefore we're going to use that to replace. Okay? And, all right, let me, before I ask that following question, does this make sense to everybody? So take every page, every physical page that we want to deal with, put them in a huge ring. And what we're going to do is we're going to have a clock hand which just has a point on the ring, and we're going to just let the clock go, let's see for you guys, tick, 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 right? And every time we tick, we're going to say, gee, was the use bit equal to 1 or 0? If it's equal to 0, we're going to assume that page hasn't been touched recently and it's a candidate for being replaced. If it's a 1, we're going to say that it's busy. And then, by the way, we're going to set it to 0 at that point. So we check the bit first, then we set it to 0. And we're going to only increment every time we need a new page. And as a result, once we set a bit to 0, the use bit to 0, we won't look at it again until the hand comes all the way around the clock. And at that point, we check it again, and we're really saying, we set it to 0, we go all the way around. If it's still 0, then nobody was interested in that page in all the time I went around the clock. On the other hand, if it is set to 1, then somebody was interested in that page in the time I went around. That's a simple idea. Okay? Questions? Because we're going to do a bunch of variants on this in a moment, but that's a fairly simple idea. And why do I say it's an old page, not the oldest page? Or why is it go ahead. That's right. By oldest, I mean least. Why is it not the least recently used page, but it's a least recently used page, a less recently used page? Go for it. That's right. It's a lot easier to just say, well, in all of this time I went around, nobody has been interested in this page, therefore it's candidate for replacement. That's what we're saying. Rather than, gee, this page was actually the oldest, in the farthest in the past, this is the page that was touched. We're not going to try to track that because that was the part of LRU that was too expensive for us. Okay? And here's a question. If I go around like that where I say, click, is it 0 or 1? Oops, it's a 1, set to 0. Click, is it 0 or 1? Will I eventually find a page, or will I get stuck going around in a circle forever? Say again? That's right. Because I'm doing this on a page fault, I've stopped everybody from running. I'm going to go all the way around. I certainly will find the first page I looked at if I go all the way around. So they'll always find something, right? Okay. Now, you can imagine that running this algorithm on the fly while I'm doing page faults might be more expensive than I'd like. And I will get to that in a moment. So maybe I'd like to basically keep a few of them free so that they're on a free list while I'm having this clock algorithm freeing other things on the free list. So you can imagine that, I'm sure. So here's another look. So this is not recently used is the way to look at this rather than least recently used. Okay? And what if the hand is moving slowly? What does that tell you? What does it tell me if the hand is moving slowly? What was that? Good hit rate. Yes. What else? So, or what is another way to look at that? Not very many misses, right? Yeah. What if, is that a good sign or a bad sign? Good sign, right? What if the hand is moving quickly? Well, that means there's lots of page faults or there's lots of reference bits set. Either one of them is means that essentially our pages are much more utilized than they should be, and we're having a hard time finding idle pages. So that means the memory pressure is high. So one way to view the clock algorithm is it's a very crude partitioning of pages into two groups, the young group and the old group. And so then you could say, well, why not partition into more than two groups? Sure. So there's something called the nth chance algorithm, which is give a page n chances before you throw it out. And the operating system is keeping a sort of a counter per page. And on a page fault, the OS checks the use bit. And if it's a 1, then we know the page is actively in use, so we clear the use bit and also clear the counter to 0. Otherwise, if it's 0, we increment the counter, and at the point we hit n, then we say the page is replaceable. So basically what this says is, I'm going to give the page n sweeps of the hand before I throw it out. And if anybody's interested in n sweeps of the hand, then the page stays in memory. Okay? So, how do we pick n? 4.5. That can't be 4.5, right? 4, 7. How do we pick n? Based on the working set, it could be. I think, yeah, it could be. I mean, a way to look about n is you're trying to decide how close you want to be to true LRU, because as n gets bigger, you're getting closer to LRU. All right? So it's a better approximation to LRU, and as n gets really large, you get a really good approximation to LRU. Okay, but it's probably not worth it. You know, why not pick a small n? It's more efficient, and exactly LRU is probably unnecessary. All right. What about dirty pages? We haven't really talked about this. One way that operating systems do an nth chance algorithm is it takes a little extra overhead. So you find a page to replace, you discover it's dirty, you got to write it to disk first before you can use it. What happens there is that occasionally people use nth chance as a way of saying the dirty pages have a little longer chance than the clean pages. And so a common approach is that clean pages have n equal 1, which is sort of the normal case, and dirty pages have n equal 2. And so if you decide that a dirty page is ready to go and n is 1, you start it writing out to disk so that by the time you get around one more time, it's already written out to disk and it's now a clean page. So, okay. Questions? So, which bits in the page table entry are useful for clock algorithms? So we talked about the use bit, the modified bit, the valid bit, and the read-only bit. So the use bit is clearly important, right? We just decided that the use bit is essential to the clock algorithm, right? It's the way we decide that a page is in use or not. Okay, now we'll question the notion of essential in just a moment. But basically the use bit gets set by hardware, cleared by software. The modified or dirty bit is set by hardware when a store goes to that page, and it's got to be cleared when the page is written to disk. So that also seems pretty important to know in hardware when somebody has written the page. Why is that? Why do we need hardware to tell us when the page has been written? So you can write back. That's correct, but what else? That is a correct statement. That isn't quite where I was going at, but that's good. So why do we want the hardware to tell us this? Yes? That's right. Good. What do you mean? It's asynchronous. What do you mean?
So when you're writing back, it's going to happen in parallel. You don't want to wait for it to write back.
Okay, now you're talking about writing back rather than writing in the first place. So the store is the thing that makes it dirty. So the store is asynchronous. So that's where I thought you were going. So the problem here is that the processor is busy doing stores to pages that you've said could be written. It's doing that. Your operating system doesn't take control and know that the processor is storing. So basically, since the processor is letting the store happen in hardware asynchronously, you got to have the hardware tell you that the store has happened. Otherwise, you have no idea that that page has been changed. Is everybody with me on that? So that's why we have hardware tell us that it's modified. Think through that again. I put a page in memory, I mark it writable, and now I turn it loose. I let a process run. How do I ever know the process wrote? Okay, I'd have to have some indication that the data in that page is now different. Well, the indication is the modified bit is set, or the dirty bit. The only other thing you could imagine doing is somehow keeping an old copy so that then you do a diff when you're about to decide whether to page or something, but that's pretty expensive, right? So the valid, of course, we've decided is important for paging in general, and the read-only is basically useful for things like code pages and so on that aren't supposed to be modified. So all four of these bits interact in interesting ways in the page management and the operating system. Okay? Are there any questions about these bits? Everybody clear on the difference between use and modified now, or use and dirty? Use just says that anybody load or store happened. Modified just says a store happened. Now, do you really need hardware modified bit? So the answer there, after I've busy convinced you that it has to be yes, is no. Okay? And the reason you don't actually need this in hardware is because what you do is you mark every page as read-only. The moment the process tries to write it, you get a page fault. You mark the fact that it's been modified, and then you set it to read-write, and you let the process do its thing, and you've now been notified that that page is dirty. Okay? So by turning something that was supposed to be writable into read-only, I can now get notified as soon as it's written. Do you really need the use bit? The answer is going to be no. Can somebody tell me how I can get by without the use bit? Yes. Perfect. You mark the page as invalid. The first attempt to either store or load from it gives you a page fault. You mark a little bit use bit in software in the operating system. You mark it as either read only or read write, whatever the correct marking is, and you're good to go. Yes. Okay, so you can emulate it the same way. And you can get the modified bit the same way, so you can actually have hardware that has neither use bit nor modified bit, but the cost is more page faults into the kernel. So you'd have to make sure your page faults are really fast handlers. Okay. So remember, however, that the clock is just an approximation to LRU. And so if we have no use bit or no modified bit, can we get a better approximation, assuming we already have to do page faults because we don't have this bit, the use bit, or we don't have the modified bit? Okay, and the answer is yes. There's something called a second chance list, which is kind of an amusing idea. And before I go there, I want to say something that occasionally happens. So you get a CPU designer, okay, and they come to their operating system team and they say, "Hi, I'm designing the CPU. Can you tell me what features are needed? For instance, do you need a use bit? Or do you need a modified bit?" And the OS team says, no, we don't need that. You say, okay. You design it that way, and suddenly they realize, oops, they needed that bit. Now what are they going to do? What happens is then the OS team has to get creative and fix things. Okay, and this particular scenario has happened in the case of the VAX. And I'm going to tell you the resulting algorithm. And basically, we're going to split memory physical pages into two categories, green and yellow. Okay? The green pages are mapped in the page table, marked as read-write, and they're in a FIFO list. Okay? The yellow pages are marked as invalid, and they're in an actual LRU list. Okay, and what we're going to do is, since the green pages are mapped as read-write, the processor goes ahead and does its thing however it wants, but of course it has no idea whether they're dirty or not. It's going to have to assume that they're dirty. And it also has no idea whether the pages are popular or not, because there's no use bit. So, how do we do this? If we go to access a page and it happens to be in the green list, we win. Otherwise, we get a page fault. And so in that case, we take the thing at the end of the FIFO list and put it at the beginning of the LRU list. We grab the page that was accessed in memory because of the page fault. If it turns out it was in memory and not on disk, we pull it off of the LRU list, put it at the head of the FIFO list. And in the rare cases where it actually was on disk instead, we page it in from disk and put it in the head of the FIFO list, and we throw out the LRU victim. So, this is a little complicated, but it's not too bad. Let's look at the two cases here a little bit carefully. Or three cases. So the first case is pages that are green, you're just accessing at full speed. So think of those as the active list that they're the ones that are clearly in use. Okay? When we page fault, we could page fault for two reasons. One, the page is actually in memory, but it's on the yellow list. Or two, it's not actually in memory. Those are two separate options here. In the case of where it's in the yellow list, we do what I said here. We pull the head of the FIFO off and put it at the head of the list. We put the end of the FIFO, put it at the head of the LRU list. Pull the page that page faulted, put it in the head of the FIFO list. What does this do? This says that we're cycling through our active pages on the green list, but by and large, we're sorting most of the pages by LRU on the yellow list. And so we're keeping pages in memory in sort of LRU order because they're on the yellow list in LRU order. And if we pull it off of disk, we have to page fault anyway. We pull it in and put it on the front of the FIFO list and throw out the LRU victim. Once again, we're keeping the pages that are actually in memory in an LRU list. Okay, and this gives us a reasonable approximation to LRU in the instance where we don't have a use bit, and therefore you're going to have to use page faults to help you emulate the clock algorithm. But this has a lot less page faults than you would if you were emulating the clock algorithm the way I said earlier, which is every time the clock hand comes around, you mark the page as invalid and wait until the next page fault to mark it valid and say the use bit is set. This will have less page faults. And this was actually implemented in the VAX. Okay? Can anybody tell me why this is called the second chance algorithm? Yes. That's right. Two chances. Which chances? That's a good guess. I like that guess. Yeah, so you start here, and when you kick it out of the FIFO list, you give it a second chance by putting it into the yellow list, and assuming you reference it again before it falls to the very bottom and gets kicked off onto disk, then you're good to go. And it's gotten its second chance because it comes back. Exactly. Good. Okay. So how many pages for a second chance list? So the second chance list, by the way, is the yellow one. So if you have 0 pages in the second chance list, then this behaves exactly like the FIFO algorithm we started out with, which we decided has Biletti's anomaly and is bad. If everything is in the LRU list, then it's perfect LRU, but you're getting a page fault on every page reference. Okay? Because every page, if it's on the yellow list, is marked invalid, and so every page access is invalid. And so every page access is a page fault, which is bad and expensive, but, gee, the pages are perfectly LRU. Okay, and so what's nice about this is you pick somewhere in the middle, obviously, and the result is reasonable. So pros are it's got few disk accesses because it goes only to disk if it's unused for a long time. The cons is that it's increased overhead dropping to the operating system over if you actually had a real use bit. And with page translation, you can basically adapt to any kind of access the program made. So this is fun. Question? Yeah, go ahead. Yeah, whatever. You can implement LRU any way that's useful. You probably do it with some sort of, doubly linked list or something that's convenient and fast. So the question is, of course, why does the VAX not actually have the use bit? And this is a case where the architect Strecker actually asked the OS people. They said they didn't need it and later got blamed for this failing of the VAX architecture. And he wanted the world to know that it wasn't his fault. He really did ask them about it beforehand. Okay. Any questions on the second chance list? All right. I want to do one more thing before we move on. So we could use the same idea with the free list. And so the idea is you take a clock algorithm. Suppose you actually have a use list. What I'm going to do is walk around, and with the clock algorithm is going to run independent of actual page faults. It's just going to run when my free list is too low, hits a low watermark. I'm going to take and run the second chance, or run the clock hand until I find a page that looks like it's not in use. I'll put it on the free list. If it's dirty, I'll start it being pushed out to disk. And then during that time, if somebody tries to reference it, I'll give it a second chance and pull it back into the clock algorithm. Okay, and so this is a way of basically keeping a set of free pages ready to go the moment you page fault. And this works very well and is used very well. It's kind of like the VAX second chance list. Basically, if the page is needed before it's reused, you just return to the active set. But most of our pages in this instance are in the actual clock algorithm. There are a few of these are FIFO managed. So this is a little bit of a twisting of that second chance algorithm on its head, but this is also one that's in common use. And the advantage of this is it's much faster for a page fault because you basically have free pages ready to go. Questions? Okay, I think it's time for a break. Let's do it. All right. So, I wanted to give you a little bit more details. Let's see, software-loaded TLBs. So do we need a use bit for software-loaded TLBs? So this kind of gets a little tricky where the hardware is actually setting the use bit in the TLB or the software manages the TLBs as a FIFO list. This can get actually kind of tricky. So if you're ever in a processor with software-managed TLBs, you have to kind of deal with it. I did want to mention one other thing, which is this notion of a core map, which is a very useful idea. So page tables, of course, we've been talking about map virtual pages to physical pages. That's been the topic of several lectures. The question you might ask is, do we need a reverse mapping, which is from physical page to virtual page? And the answer to this is yes. Okay? And when you think about it, the clock algorithm is running through page frames and then it decides, oh, we're going to page out this page. Now what? Well, now it's got to figure out which virtual page in the page table to invalidate. Worse, if there's 2 or 3 processes that all have the same page mapped, you got to figure out all of the page tables that have that page in it. Okay, and so that's what the core map does. All right? Because you can't really push the page out to disk without invalidating all the page table entries, or you're going to end up with some pretty weird behavior. So then the last thing I wanted to talk about in this topic before we kind of move on to I/O in general is sort of how do we allocate memory among different processes? Does every process get the same fraction of memory or different fractions? Should you completely swap some processes out of memory or not? And obviously each process needs a minimum number of pages, and you want to make sure that every process that's loaded into memory can make forward progress. So for instance, if you got a process that stopped on a load instruction and it needs at least how many pages? 2, right? 1 for the instructions and 1 for the data that are being loaded. Otherwise, that instruction is going to fault. Okay, so you can kind of see where this minimum comes into play. However, this can get more interesting, like the IBM 370 architecture. It maybe needs 6 pages because there's a string move instruction. The instruction, 6 bytes, it might span 2 pages, 2 pages to handle the from, 2 pages to handle the to. Okay, and so it's not always just 2 pages. It might be more depending on the architecture. Now, of course, we're talking about a small number of pages, so a conservative operating system could pick a number like 10 or whatever, or 8, and probably be okay. All right. So what are some replacement scopes? So when we go to replace pages, we've been kind of talking implicitly about a global replacement policy, which says when a process page faults and it needs to bring data in, I'm going to select a page among all of the processes that are running because everybody's in the same clock. I put everybody's pages in the same clock. What's the alternative, of course, would be a local replacement policy where I only replace my own pages. So everybody's pages are in their own clock. And so I replace among my own pages. And then there's some higher level policy of choosing which process gets how many pages. Can anybody think about pros and cons of global versus local? Yes.
Global kind of acts like LRU across processes that are being scheduled. So someone hasn't been scheduled for a long time. There's not page down.
Okay. So I think what you want to say is it's adaptable. It sort of adapts the partitioning automatically between processes as they change their use patterns. How's that say? That's what I thought I heard you say. Yeah. Okay. When would local be more desirable? Yeah. Yeah. When you want to start worrying about guarantees or denial of service, then maybe you do want a local allocation policy which says that at worst I affect only myself. But then, of course, you got to have a good global allocation policy on top of it. Yes, good. So We can talk about fixed schemes like equal allocation, where every process gets the same amount of memory. Excuse me. 100 frames total, 5 processes, everybody gets 20. We can talk about proportional allocation. So the larger processes get more memory. So this first one seems like a fair share kind of scenario, right? This latter one's a little tricky, but you sort of say, well, the size of the process P is SI pages. Excuse me. And we come up with some scheme so that larger processes get more physical frames. Seems on the face of it like it makes sense, but maybe bad idea. Why? Can anybody see a pretty fatal flaw with this scheme? Yeah. Yeah, you inflate your process size. I'm going to link in 12 other libraries that I don't actually use, thereby making my process much bigger and faking out the proportional allocation to give me more physical frames. Yes. We could give some sort of priority scheme, okay? Process PI generates page fault, select for replacement of frame from a process with lower priority. That kind of makes a little bit of sense, right? You're giving priority, higher priority processes more pages. All of these schemes have their problems, all right? And I would say that what actually happens in most operating systems that are not specialized is that everything is kind of put into a big pot and you sort of try to set limits on how much memory things can get. And other than that, they try to flow across the pots of memory. And the downside of that is that these kind of denial of service bugs that may not even be intentional show up, which you could cause one process is swapping like crazy and slows everybody down. All right? But this is one of those things where there aren't a lot of good options that have been presented in sort of commercial operating systems. And maybe you got to use some sort of adaptive scheme to figure out who needs what. So let's finish up a little bit. Can we? I have a couple other little random topics. So could we reduce capacity misses by dynamically changing the number of pages per application? So I thought this is kind of interesting. Remember earlier we were saying we would prefer a page allocation scheme that gave us this kind of curve where we added more page frames, then we got a lower hit rate. Got a lower miss rate, and if we added frames, we got a higher miss rate, and so things were monotonically decreasing to the right. Then we could somehow pick the right amount of memory. So in this scenario, you could imagine what you actually want is to find an optimum that's somewhere between a lower and upper bound. You don't want to have so much memory that the hit rate is so low that you're wasting memory. So much memory that the hit rate is so high that you're wasting memory. And you don't want so little memory that your hit rate is so low that you're thrashing all the time. You want to be somewhere in the middle there. And so you could dynamically adjust the amount of memory given to a process based on its miss rate. Does that make sense to everybody? Sorry, I'm getting a little tongue-tied. It's close to spring break. Okay, so we sort of decide what an acceptable page fault rate is and then put ourselves in the middle here somewhere. And why do we not want to be way over here? So this is a scenario where this guy has got a super high hit rate or very low miss rate. Why is that maybe not the best way of using memory? Say again? Well, it's using a lot of memory. Why would that be bad? There you go. That's only bad if we're competing with somebody else who could better use that memory. Okay, so this particular statement I'm making here has got to be in the context of an optimization problem with at least two processes involved. But if we have competing entities needing memory, it's possible that giving this amount of memory to this process is really not a good use of that memory. It would be much better to give it to some other process that's in this part of their curve. And so that's the kind of optimization that you could imagine. It's a pretty nice dynamic one. Okay? What if we just don't have enough memory and everybody's kind of in the high part of their curve where they're just missing all over the place? Then what? Yes? Okay, very nice. So wouldn't it be good to temporarily put a process on hold, confiscate all its memory, let the other guy run for a while, then load that other process? Yes. Good. So obviously you've heard the term thrashing. Okay? Thrashing is used for many things. When it's talking about paging, like we're talking about, it's this phenomena where when you got too many processes, so they're filling up memory, so the demand of memory is too high, you suddenly get a point where nobody's making progress. And so the way to interpret this curve is as we increase the number of threads or processes, we're getting better and better utilization because we're overlapping computation and I/O until we fill up so much memory that we're doing nothing but paging in and out to disk all the time, and then everybody suffers and we fall off. Okay, and in that scenario, this is called thrashing, and basically it's all overhead. The only thing we're ever doing is pulling a page off of disk, putting pages back on disk, sitting on the wait queue, then on the run queue for one load or store, and then we're back on the wait queue. And the question is, how do we detect thrashing? What's a detector for this? Probably something to do with how long you're running, right? Or if everybody is kind of in this mode where nobody's running and they're all waiting on disk I/O, probably, right? And what's the best response to thrashing? Well, we heard a great one earlier. Maybe the right thing to do is to put some processes completely to sleep by swapping them entirely out to disk so that others can run for a little while and then pull them back in. So this is one of those rare instances where actually swapping a process entirely to disk and then back into memory is better overall than letting it stay in memory. Okay? All right. And so then the final little topic here is I wanted to show you this. So program memory access patterns have some temporal and spatial locality. If you were to follow that little pink bar, should we try that again? Ready? Watch carefully. Okay? What you would see at any given point in time, did you guys all catch that? All right, let me do it again. All right. I'm just kidding. So if you're looking at a slice of time in the bar, at any time you see the addresses that are in use, and at any point in time the groupings of addresses that are in use are the working set. And really the indicator of thrashing is when the active working set, so what we see here, for instance, is this group of addresses are in active use at this time. If I take the working sets of all the processes and put them together and they don't fit in memory, then I'm thrashing. Okay? And the working set really defines the minimum number of pages needed for a process to behave well, and not enough memory for the working set is thrashing, and that's the case where it's better to swap somebody out. And there is a simple working set model, which I'm sure you guys have seen before. They probably mentioned this in 61C, I'm guessing. But the example here is take all of your references and define a window size, like, for instance, of 10,000 instructions. That's just a number I picked out of the air. And you could say, look at all of the references in the last 10,000 instructions. All of those addresses are my current working set. And then you let that window slide in time, and that's how the working set changes. Just like that little pink bar went. Okay? And so we can basically say that in terms of approximating what the working set size is, if this delta is too small, we're not really seeing what the active working set is. And if it's too big, we're not really changing enough, so you can adapt delta a little bit. But the bottom line is, if we sum up all of the working sets for all the processes, that's the total memory we need. And if the total memory we need is greater than the memory we have, we're thrashing. Okay, so you can actually define thrashing mathematically in terms of the working sets of all the processes that are in memory. Okay, and we mentioned working set last time, so I don't need to go into it. But were there any questions on this? Now, this is clearly an experiment that you could run after the fact if you were to sort of take a bunch of page references and post-process them. But you can also do this online. So with every page that gets pulled into memory, every time there's a page fault, you can keep statistics. And every time you page out something or it's not used for a long time, you can keep other statistics. You can actually track the working sets of processes in the kernel online, and then you can make some memory decisions based on that by saying deciding sort of which processes get which amounts of memory. And so the last thing, of course, is what about compulsory misses? If you remember, compulsory misses are misses that happen the first time a page is seen and hasn't ever been in the cache before. And if you swap a process entirely out and start it running again, those are all misses that are kind of compulsory because the thing's been swapped out for so long, you bring it back in, now it's going to touch a bunch of things for the first time again. And we can do a lot of things to help that. So on a page fault of a process that's just been restarted, we can bring in multiple pages around the page to try to avoid compulsory misses because of spatial locality. We can also track the working set like I mentioned earlier, and then when we swap a process back in, we can swap in the working set pages as a way of sort of eliminating these faults. Okay. These are all possibilities. All right. So we are here. We've kind of finished up with address spaces, and we're about to pop into file systems, which is a fun new topic. And to do that, we're going to be talking about I/O. And what I want to do is do a little introduction to I/O here in our last few minutes, and then we'll pick this up after spring break when you guys are all fresh from relaxing, which you're all going to do. So if you remember, we talked at the very beginning of lecture about sort of the scenarios of pulling programs into memory and executing them on a processor, and part of that was interacting with storage like disks or networks of various sorts, wireless or wired. And really, we've completely ignored this whole I/O thing, right? I mean, this I/O bus and controllers and all of the complexity involved in making that I/O work seamlessly has been kind of not a topic so far. And that's what we're moving into. We're going to really talk about these topics in more detail. Kind of in a picture, you can sort of say, well, all right, this is fun. There's a processor with multiple cores and an L3 cache that's shared. But we're really talking now about outside the processor where there's some I/O controllers that we send commands to. Those I/O controllers connect either with wires to devices, or maybe they're wirelessly connected. These devices use direct memory access to transfer data from the device into memory. And then we read and write that memory, just as if we were looking at the original cache data. This path is an interesting one because there's a lot of control in that. How do we talk to the controllers? How do we decide how to set these DMA transfers up and so on? Okay. So what are some of the requirements of the I/O? Well, so far in this course, we've really learned how to manage CPU and memory. But what's interesting about I/O is, first and foremost, without I/O, computers are useless. Okay? I've been a computer architect for a long time now, and it is interesting when people who are focused only on CPUs talk only about the CPU, and they forget, well, if there's only a CPU and maybe it's got some memory, it's pretty pointless. That's a disembodied brain that's not doing anything with the world. Okay, so the I/O is a pretty interesting part. And the downside, or the unfortunate part, which may be why a CPU designer doesn't like to think about it, is there's thousands of different devices, everyone's a little different, and you start wondering, how can we come up with any standards at all that allow them to interoperate with each other, right? Every one of your USB keys is different, every little disk is a little different, every keyboard's different, every screen is different. It's a mess, right? And devices are unreliable because disk blocks fail, there's transmission errors, and so on. And you might ask yourself, how can we make them reliable? How many of you realize that when you store things on a disk on your laptop, there are errors all the time that are masked for you? Okay, with today's disk drives, the density is so high that there's no way that every bit that's stored on the disk comes off. Instead, there's redundancy in the form of Reed-Solomon codes and other interesting error correction codes that make sure that you pull off this faulty data and you get back what you wanted. Okay, even though there's a bunch of errors. All right, that stuff is masked partially inside the drive controller and partially in the operating system. And of course, the same is true about the network. You're getting lots of failed packets when you communicate with websites. Devices are unpredictable or slow. That's also a problem. Some operational parameters are some items you talk to with bytes. like keyboards. Some you talk to with blocks of data like disks. Some files you look at sequentially, like you're about to watch a movie, which is the first thing I'm sure you're all going to do after this class. You're going to watch the class again. It's sequential, right? Or random, you actually access things random. Yeah, go ahead. Question. I don't know how to answer that question. This idea of sequential versus random is an important one because it turns out making things sequential is easy. Making the ability to randomly address them is going to be tricky. And then, of course, there's also this question of how do you even get notified that something has happened? Do you get polled? Do you have to poll and see, are you done yet? Are you done yet? Are you done yet? Are you done yet? Or do you get an interrupt? These are all things we're going to talk about. And just to give you a little flavor, what's interesting is if you look at, say, the Linux kernel or similar kernels, Pintos, whatever, there's basically this system call interface that you're used to and you get to play with a bit in Project 2. Below the surface, that system call interface leads to a bunch of interfaces, some to do with processes, which you're already familiar with, some to do with memory management, like virtual memory, some to do with I/O, like file systems and keyboards and networks. These devices have sort of a top half and a bottom half, and we're going to talk about the interesting parts of how that's organized. Okay, so that's up for spring break, but I don't want to delay you anymore. So just to recall, precise exception says there's a single instruction for which all previous instructions have completed and no following instruction have actually started. We talked about these sort of back-of-the-envelope replacement policies, FIFO, MIN, and LRU. And then we actually talked about a real implementation of LRU, a real approximation, namely the clock algorithm. We talked about the nth chance version of that, and we also talked about the second chance list. We talked about working sets, which is the set of pages touched by a process most recently. We talked about a model for thrashing, which is basically, the bottom line, you don't have enough memory. And we started to get into I/O devices. And what we're going to find out is there are many devices, many speeds, many access patterns, many timings, but only one kernel. We'll figure out that after spring break. Have a great spring break, everybody. May the net force be with you. F equals ma. Rules the universe except where it's extremely dense or you're going very fast. We'll see you later.